Alright guys, so in our last video we were able to show um examples on modules, and in this video we'll be dealing with some of the important examples in modules and their provings. So we have the first one. Any abelian group is a module over the ring of integers. So we let R be equals to Z such that n will be in R and a will be in A. Don't forget scalar multiplication. So we check n a, that's we check for the additive for when n greater than 0, and when n equals to 0 we have 0, and for negative a as well, that's for when n less than 0. So we suppose that a is also a Z module for all nx in R. Ns simply means we are picking scalar, two different scalars in R and two different scalars in A, and as such we have n plus x a, that's equals to a plus a plus up to n plus s times. So like the first one we have, you see we have up to n times, but in this case we'll be having n plus s times. Then we'll open our bracket. On open the bracket, we separate n times and s times respectively, and as such we have na plus sa. So it implies that n plus x equals to na plus xa. That's answer number 1. That's the first answer for this one. Then the second answer is n equals to a plus p. So we go the same way. We have now a plus p is representing our scalar. Of course, a plus p is in a plus p is in a, y n comma x is in R. So we have it that a plus p, it keeps on going up to what? Up to n times, and we separate it again. We separate the a's and we separate the p's up to n times, and we have that to be na plus np. That's answer number 2 satisfied. Then answer number 3, that's nxa. So this simply means that a is representing our constant value, and we have that a plus a up to ns time. So ns time is outside of the bracket, so that's ns time. So we use the same approach now, but this one is slightly different from the other ones. You can see that a plus a up to s time plus a plus a up to s time, sorry, it is meant to be a plus a n times, then a plus a s time. So I think that's a slight error. So you change the first s time to n times, not s time. So but everything all together is in n times. So we have that to be xa plus xa up to xa, and all together again they are in n times. So we have different ways of doing this, but this is one of the approach of doing the proving the third axiom. So that's nxa. And for the last part, since there is an identity, then it simply means that 1a equals to a for every value of a in a. So that is that. So the second one deals with the set of matrices, the set of m times n matrices over the ring. Now m times n matrices, we have that aj, aij, bij, and cij, three different matrices, such that when they are being added, it is a plus b equals to c, and c is in n. We already said that n is an abelian group. So since n is an abelian group, we can have it that Cij will be Aij plus Bij. So we are picking two different scalars again, that is nx in R and AB in N. So when we apply the axioms, we have our final answer. We show clearly that N is an R module over R. So the next one, the set of all polynomials is also an R module. Set of all polynomials is also an R module. That's Rx. So of course, you know, from vector spaces and ring and from group, you already know the defined value of polynomials. So we pick Q and P and Q, and that's Q naught up to Qn xn. So you apply the four axioms as well. Axiom 1, axiom 2, axiom 3, but you have to be very careful when applying the axioms. You must follow the step. You must not skip any step when applying the axioms. So you can see axiom 1, that's APX plus AQX. Axiom 1 satisfied. Axiom 2, APX plus BPX. Axiom 2 satisfied. And axiom 3, ABPX satisfied. And since there exists an identity, it simply means that 1px is equal to px. So that's that for that. So the last one, I'll be giving you one. You do the last one. You show that one yourself. That's every ring is every ring R is a module over itself. So you do that one yourself. Then the last one, the set of real number is a left arrow module. The set of Rn is a left arrow module over itself. So we pick arbitrary values from R. Since you know R is a set of real numbers, we pick x1 to xn, I representing the values of n respectively, and we pick two arbitrary values x and y, and we apply the axioms. So this axiom is you have to follow the step. So you see, we start from x1 plus y1, then we reduce to rx1 and ry1, and at the end of the day we have axiom 1 to be rx plus ry. So that's that. So you can go through the second axiom. It is well explanatory as well. That's the second axiom. And the third axiom, rxx, and the fourth axiom. So you can just pause the video, and go through the axioms very well. So those are the basic example under modules and vector spaces. So just go through the example and pause the video. So in our next video, we'll be checking out on submodules. Thank you.